Okay, I'm going to do a video here on this 4.2 through 4.5 mix. So after getting done with 4.5 and trying all the homework, um, it's going to be good to kind of do, I guess, this sort of review mix assignment. And I think I'm going to be pretty thorough here, I guess, but at the same time, I guess I'm assuming you already tried this yourself and you're going to kind of see how well you did and kind of use this as a supplemental, sort of resource to compare your answers, or if you got stuck or something. Um, so hopefully all of this stuff from 4.2 all the way through 4.5, hopefully, it's things have now come like full circle, and you've kind of like digested all of this pretty much new material. And so this will be a pretty good review. I I gotta think. Just going off of my memory right now, there was probably like every once in a while on those homework assignments, like especially from 4.4 and 4.5, there was probably like a handful of homework problems that were just crazy. But this set of problems should be a pretty good, I don't know, like a nice, look at, just kind of like the average type problem. Not way too easy, not way too tough. Anyway, so number one, I want you to find a power series that represents this function. Well, I hope you look at this function and see how it basically matches up with a sub 1 all over 1 minus r. So that would make our first term 1, 1 minus 3x, and that would make our common ratio. It's geometric. I don't know if I said that yet, but you can pretty much model this as a geometric series because it would represent that function which matches this whole geometric thing. So on negative 1/3, 1/3. Now this interval is only going to make sense because of that being the common ratio. But anyway, so that means the power series would basically go, 1, and then 3x, and then 3x squared. You could simplify that obviously to 9x squared, and then 3x cubed, because you're always multiplying by 3x to get to the next term. So I guess one way to write out this series is just kind of write, the first handful of terms and then plus dot dot dot. And you might actually sort of technically need to include, something like that, is like, but it's better to maybe like take this and kind of put it in a sigma representation where, let's see, if we're going to go with 3x to the n, and we're obviously going to infinity here, are we going to start off with 0 or 1? Remember, our first term has to literally equal just 1. So I think we're going to need to start off with n equals 0, which is pretty common. And I think that's it. Number 2, find the interval of convergence and the function represented by this series. So we could go with the ratio test, right? We could go with the ratio test, But I'm looking at this and I can tell, I don't know about you, I can tell that this is geometric. And so instead of using the ratio test to find this interval of convergence, I think I'm going to do the whole geometric test type routine. Now you could write out the first handful of terms here, plug in 0, then plug in 1, then plug in 2. But I'm pretty sure that the R value here is going to end up being 1/2 x. Okay? I can tell, I don't have to write out the first handful of terms to realize that just from this sigma definition that our R value is going to be 1/2 x. So guess what? How does the whole geometric test work? Well, a geometric series converges as long as your common ratio is in between -1 and 1. And so when we finish solving this for x, multiplying everything by 2 to solve for x, here is our interval of convergence. All right? Now, it occurs to me, what I'm about to do is investigate the endpoints. See, by the time we got all the way done with section 4.5, we sort of realized that in order to be thorough, we needed to kind of investigate and check the endpoints. See, right now it's just less than, and this is just less than. So as I was saying a minute ago, it occurs to me that with the ratio test, this is what you have for like converging absolutely. And then when you check the endpoints, that's maybe checking for like conditional convergence. But anywho, let's, just out of curiosity, let's check the endpoints. Let's check the endpoints. So if we were checking at exactly -2, I might as well write it down, x equals -2, that would result in, let's see, if x were to equal -2, we would have 1/2 n plus 1 times -2 to the n power. Okay? And this would end up being geometric. And I'm pretty sure that the common ratio would end up being -1. So our common ratio here, and this is also a geometric test, really. I mean, you can check this by the geometric test. And this flat out does not converge because your R value is exactly -1. What if our x was, let's see, our other endpoint was exactly 2. So if we plug in +2 for x, I'm not even going to write that right now, we end up with literally 2 to the n. And this is also geometric, and I'm pretty sure here that our overall R value would be +1. And based on that geometric, test check, this would not converge. So it would not converge at exactly -2, and it would not converge at exactly x equaling +2. So really, this is our final interval of convergence. It converges strictly in between -2 and 2, and not at exactly -2 nor +2. And I mean, if you were getting like really in depth with it, does this converge absolutely or does it converge conditionally? Well, I think you could say it converges absolutely, because if you threw an absolute value, on all this stuff, it would converge there. So technically it converges overall here, as you know, or you could say it converges absolutely. Now the other half of this question was the function that this is represented with, you know. And so remember this whole geometric thing, you use this as a template for the function. So we have our first term. What would our first term be? If we plugged in 0, I think we would get 1/2, right? That would be literally our first term. By plugging in 0 in for the ends, we would end up with 1/2. And remember, our common ratio was 1/2 x. All right. And I mean, this is pretty ugly, you know, as far as like having a final answer. So the only other thing I would do here to kind of clean it up is kind of multiply the entire top and the entire bottom by 2. Like multiply the entire nasty looking fraction by 2 over 2. And 2 times 1/2 is 1. And then 2 distributed through the whole bottom would be 2 minus x. And so I think this would be maybe a pretty good final answer for like the function, right? Or, you know, y, or is y equals all of that, or f of x equals all of that. Okay? Woo, number 3. So hopefully that all landed on camera in the screen correctly there. But so number 3, get out of the way. Find a Taylor series. Oh, not just the polynomial to like 3rd order or 4th order or something, but the Taylor series for this. Oh, my kryptonite. Let's see if I forget to do this correctly, because it's not x equals 0, it's x equals 1. So here's what we do. I know we're not actually required to give the Taylor polynomial, but that's kind of what we're going to do so that we can figure out the Taylor series. So there's our original function, and f of 1, because we're going to be plugging in 1, f of 1 would equal e to the 3rd. Yep. So e to the 3rd, and then if we do f prime of x, the first derivative, we get e to the 2x plus 1 times, you know, tacking on the chain rule. So the derivative of 2x plus 1 should be 2, right? And so if we now plug in 1 to that, we will get 2 times e to the 3rd. Doing the second derivative, we're going to get, let's see, so we're going to get like 2e to the 2x plus 1, but we have to tack on chain rule again, and so overall it's going to equal 4 e to the 2x plus 1. And when we go ahead and plug in 1 to there, you're going to get 4 e to the 3. Let's do like maybe one more at least. For the third derivative, let's see, if we take the derivative of this, it's going to be 4 e to the 2x plus 1, but tacking on another chain rule, and so we get 8 e to the 2x plus 1. And then when we actually plug in 1, we're going to get 8 e to the 3rd power, right? And you know, that's how things are going to kind of play out. If we took the fourth derivative, I can pretty much bet that we're going to get 16 e to the 3rd. Anyway, so the first handful of terms, let's see, to go, oh, here we go. I don't want to forget and look like an idiot again. So we're going to have in our terms, I guess I can write it down here, huh? I got a lot of space. So we're going to have like x minus 1 to the 0 power all over 0 factorial. But along with that first term, we're going to have e to the 3rd power, because that was the answer. And then in our next term, it's going to be x minus 1 to the 1st power over 1 factorial. But along with that, we're going to have what? 2e to the 3rd? Should have left myself more room. 2e to the 3rd. And then in our next term, we're going to have what? For the second order, we're going to have 4e to the 3rd along with our x minus 1 to the 2nd power all over 2 factorial. And then for our 3rd degree, we're going to have 8 e to the 3rd x minus 1 to the 3rd all over 3 factorial. Now this, I'm pretty much out of room, but that keeps going, literally forever. This is what? These terms would be like the 3rd order Taylor polynomial. And look, I'm sure we can clean this up, right? 0 factorial is just 1, that's just 1, that's 2, that's 6, and then things reduce and stuff. So you can obviously clean this up, but remember the rule of thumb. The more you clean things up, the more you lose where all this stuff came from, right? I mean, like take this 4, for example. Where did that 4 come from? How did that 4 get created? Wasn't it like 2 and then times 2 again? How did that 8 get created over here, right? And you got to trace it back to the beginning. Where did this 8 actually come from? Didn't this 8 sort of get created by doing like 2 and then times 2 again, then times 2 again? So you could think of this 8 not so much as 8, but technically 2 to the 3rd power. Just like you could technically think of this 4 as 2 to the 2nd power. And this 2 is technically 2 to the 1st power. And then couldn't you technically say that over here we had like a 2 to the 0 power? And that, ladies and gentlemen, helps us create our final answer, our Taylor series. Because in every single one of these terms, aren't we going to have like 2 to some power? So 2 to the n power, starting with 0. So 2 to the, see, we're starting at 0. So 2 to the n makes sense because we're literally starting at 0. And then we're always going to have an e to the 3rd, like literally every single time, as well as an x minus 1 to the n power, starting at 0, all over, n factorial, starting at 0. And that's the final answer, ladies and gentlemen, to number 3. Oh, brother. Number 4. Find the interval of convergence. So I think on this mix, I think this is the only time we're doing the actual interval of convergence and not just does it converge or does it, diverge. Okay. So we're going to do the ratio test. The ratio test. Because usually that's the go-to to find this interval of convergence. So remember, it's going to be an overall. This is how the ratio test works. We do a limit as n approaches infinity. And we got to do a sub, remember it's got to be like a sub n plus 1 divided by a sub n. So, instead of all the n's, we're going to have like n plus 1. Here we go, baby. N plus 1 times, now, I mean, I didn't forget, but I shouldn't go any further before I tell you that, remember, I'm going to remind you that with the ratio test, we have to throw in absolute value. And so at first, we're checking for absolute convergence, because the ratio test, you're not even allowed to do it unless you have all positive terms. So we're going to technically have that absolute value, and then 4 to the n plus 1. Holy moly, look what happens here. We have n plus 1 squared. Holy crap. What a mouthful. And so now we're going to multiply by the reciprocal instead of dividing by the fraction. So we have to flip it, and we're going to have n squared plus 1 all over n, and then, hey, we got to throw an absolute value on that x, right? Okay, here we go. Infinity. So when you cancel absolute value of x to the n with absolute value of x to the n plus 1, we're going to have just the absolute value of x. On the bottom, well, what else? The other thing that cancels is like 4 to the n is going to cancel with 4 to the n plus 1 to just pretty much say 4, right? Right? Nothing else cancels right now. I mean, it's probably not going to cancel at all, but I'm not going to. So everything else like this, so up top, this like n plus 1 will just kind of come on down. So that n plus 1 along with this n squared plus 1. And then down here, holy moly, along with the 4, we're going to have that n. So that n comes on down, along with this really crazy n plus 1 squared plus 1. Now I know this looks nasty as all heck, but I mean, look, overall, you got to realize that now that we're actually going to like let n approach infinity, up top, if you were to actually FOIL all that together, ultimately you're just going to end up with like 1 n cubed plus, yada yada yada. Down here, you're going to end, I mean, you got a 4 down there. So when you actually FOIL all that, again, I know this looks messy, that's a 2. You'll have like n squared here with a bunch of other stuff, but then multiplied with this 4n, you're going to have like 4n cubed plus blah blah blah. So ultimately, letting n approach infinity, you're going to end up with 1/4, 1 over 4. Now along with this, you're going to have essentially all of this equal the absolute value of x over 4. Now, what does the ratio test say? The ratio test says that this will pass that convergence test as long as it is less than 1. So we now keep solving this, and we end up with this as like a first draft, so to speak, of our interval of convergence. So remember how absolute value works with inequalities. You multiply 4 to the other side, and then you have this, and then which that basically means is that we are in between -4 and 4. So this is where it converges absolutely. Okay? But now we have to check the endpoints, remember? You got to be thorough here, man. We have to check literally the endpoints. So at x equals -4. Holy moly. So when we literally let x equal -4, we have n, and then like -4 to the n. Someone's trying to call me. Anyway, all over, geez, 4 n squared plus 1. Anyway, what we have here, gang, overall here, is an alternating series. Okay? And so so this is now technically, I mean, we have like -4 to the n, all over 4 to the n. We essentially have, like, with these two things together, we have like -1 to the n essentially. So this is an alternating series, and we can run the alternating series test. Remember how that works? So focusing on just the n over n squared plus 1, okay? Does n over n squared plus 1, is that always getting smaller, and is that approaching 0? Just like the terms, n over n squared plus 1. Yes. So this actually converges by the alternating series test. Now if we let x equal +4, okay, so these kind of cancel out, and you're left with just n over n squared plus 1. Okay? Now, I don't want to drag this out any more than I have to. Let's just say that checking n over n squared plus 1, I mean, it's not a p-series, not geometric. You can't. I think what you'd have to do with like n over, I mean, you could try the integral test here. Because again, listen, this is not alternating. This was an alternating series. This was just end up being n over n squared plus 1. So I think you'd have to do one of the comparison tests, or maybe the integral test. I don't know. You could check the graph. But I think if you were to run, say, like the limit comparison test, yeah, what could you compare this to? You could compare it to, let's see, n over n squared plus 1. That's just comparable to n over n squared, which is really just 1 over n. So you could like do the limit comparison test, I believe, comparing it to just 1 over n. And it turns out that it's going to diverge by the limit comparison test. So that means it did not converge conditionally at 4, but it did converge conditionally at -4. And so the overall final interval of convergence overall, right, is that. Okay? Converging absolutely on that interval, converging conditionally at x equals -4. Goodness. All right, number 5. Number 5. So now we're just doing converge or diverge, period. And this is where you would now have like your list of all the different tests. Maybe starting off with geometric or nth term test, or if it was like a p-series, you know what I mean? And you have like kind of this hierarchy, this order of which test you try first, and then others you try as like backup plans. It turns out the number 5 is geometric, with r equaling 1/8. So this is actually geometric, with r equaling 1 over 8. And so it turns out that this, because, the R value is the right kind of R value for a geometric series converging. So this converges by geometric series test. So we didn't even, I mean, maybe this could be also done by some kind of comparison test, or, you know, it's always possible that more than one test will apply. Usually there's probably more than one way to skin the cat, so to speak. But luckily, one of our early tests that we should probably be trying worked out. Number 6. Okay. Let's see here. Nth term test. Inconclusive. Oh, shucks. Geometric test. Nope, doesn't apply. This is not geometric in nature. It's not a plane like P series. Ratio test? No, I mean, just trust me. I don't know if this is something that looks like where a ratio test would apply. I mean, maybe it would. I don't know. But let's try one of the comparison tests. So what would you compare this to? I mean, again, if you chop away stuff, 4n over n cubed, which, pretty much evolves into 1 over n squared. Okay. So we could compare this to 1 over n squared. Now we know that this is a p-series that converges, right? That's pretty easy. So maybe let's try the limit comparison test. Remember how that works? Wait a minute, are we allowed to? Positive terms, blah, 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 blah. Yeah, this should work out. Yeah, so we're allowed to do the limit comparison test. So remember how that works? We do like a sub n divided by b sub n. So let's multiply by the reciprocal. Okay. And so this, I mean, you know what, I'll actually go ahead and actually multiply this together. 4n cubed minus n squared all over n cubed plus 1. Hey, a very basic limit, especially if you're letting n approach infinity, that's just going to equal 4 over 1, or 4. Now, remember what it means in the context of the limit comparison test? If we got an answer anywhere between 0 and infinity, our series is going to do whatever the comparison series does. So our series converges by limit comparison based on how we got this as our limit. Okay? Oh, number 7. I like it already. So what test could we apply? Could we do nth term? No, it's inconclusive. Just because the individual terms approach 0 doesn't mean diddly squat. Sorry. So it's not geometric, but guess what? It is a p-series. So this one will be over before you can, blink your eyes, I guess. I don't know. I don't know what I was trying to say there. This will be over really quick. So since our p-value here, it is a p-series, and since our p-value is 1/2, what does that mean? That means it diverges by p-series test. That one was just that easy. Final page. Okay. So, let's see here. Nth term, it's not geometric. It's not a p-series. You know what, gang? I'm going to try ratio test. And my Q was this power. You know, like when you see factorials or exponents of n, that's a pretty good, Q to do ratio test. Maybe you've already sort of caught on to that. I don't know. But I'm telling you now, when you see powers of n or definitely factorials, that's going to be a pretty good cue to do our ratio test. Now, we're allowed to do ratio test because I think we're only going to have positive terms. So here we go. The ratio test involves a limit. And remember, we got to do like a sub n plus 1. So this is going to be 2 to the n plus 1 all over n plus 1 plus 1. Okay? And then times. Okay? So there's not going to be any canceling here, but there will be some canceling here. So we're going to end up with, let's see, 2, just a 2, right? Just a 2. And then the n plus 1 is still there. Nothing happened to it. And then down below, I think we're going to have this n plus 1 plus 1, or in other words, n plus 2. So now, actually taking the limit, letting n approach infinity. Let's see, this is going to be like 2n plus 2 all over. This is a pretty basic limit you've been doing since last semester. It's just going to equal 2. So what does that mean? In the course of this ratio test, getting a final limit of 2, what does that mean? Well, since 2 is greater than 1, that means according to the ratio test, it's going to diverge. Mwahahaha. Number 9. Number 9. Okay. Let's see here. It's not a p-series. I mean, it's close to a p-series. Maybe that'll be a comparison thing later. It's not geometric. Yeah, let's try a comparison test. Okay? So this is technically 4 over n to the 2/3. So you know what? Let's compare this to just 1 over n to the 2/3. Because this is just a p-series. Okay? So what is this series? Does it converge? Does it diverge based on the p-series? Since your p-value is equal to 2/3, that means this is going to diverge. Okay? So we could do we could try a limit comparison, but let's do a direct comparison. Okay? How does 4, let's again, remember direct comparison was if your series could be shown to be like smaller than something else that converges, then you're good to go. Or, what we're comparing to is a series that diverges. So if we can pretty much show that this is going to be bigger term by term than this, then we could say that this also must diverge if it's bigger than something else that diverges. So, heck yeah, 4 over n to the 2/3 is absolutely going to be bigger than this. Because, this has a numerator of 4, this has a numerator of 1, so this has a bigger numerator. So yeah, this checks out. So we can now say that our series diverges by direct comparison. You know? On a side note, I think, I'm going with my gut here, I'm pretty sure that instead of doing the direct comparison, you also could have done the integral test. So if you got an answer, right, by doing an integral test, you were probably correct. Okay? Because I think with the, well, if you have any questions about using the integral test, just let me know. But I'm pretty sure you could have also done integral test to figure out that it diverges. Okay? So, number 10. Last one, number 10. All right. Once again, I would not doubt if you could figure out number 10 by doing more than one different test. But let this be a lesson to you. What are the first tests that we're probably trying really quick? P-series test? No, it's not a P-series. We could maybe compare it to a P, I don't know. But it's not geometric. But what's one of the other tests you should probably try first really quick? The nth term test. So let this be a lesson to you. Don't forget about the nth term test, people. If you just look at what these terms are doing, what are the terms limiting to? 3. If the terms themselves are limiting to 3, like they're not even limiting to 0, they're limiting to 3, then that right there is a deal breaker. And we can just go ahead and say that this series is going to diverges by nth term test. That's right. Don't forget about the nth term test. Now look, on any of these, like I said, it's definitely possible that more than one test works. Like I said over here, number 9, direct comparison worked. Integral test would have worked, maybe limit comparison for all I know. If you did this assignment and, tried other tests and you just wanted to confirm with me that you did the right thing with whatever other test you tried and it seemed like it worked out or you're not sure if it worked out, then just let me know.